Okay, well, on Wednesday we won't be meeting because it's assessment day, and that's an opportunity for programs to assess the efforts in the department and how well we're meeting our objectives. You know that ABET, who is the entity that issues our accreditation, has a pretty strict and rigorous set of guidelines for how we assess our students, our graduates, and so forth. And so we'll be meeting to, not you and we, but the faculty will be meeting to discuss assessment. And I think the university has some assessment day activities they're encouraging you to participate in. Usually they provide a free lunch over at the Student Center. So I imagine you'll be getting emails about that if you haven't already. As a reminder, Lab Demo 1, which was for those activities we did on Friday related to the broad-crested weir and sharp-crested weir, that's the calculations for it will be due on Friday. And then your final project submission is due on Friday, the 12th of April. So we've got just about 2 weeks remaining for that. Any questions on the announcements?
What are we doing Friday for those that are missing this conference?
You'll have to watch the class online.
But there's not another lab demonstration or anything?
No, the lab demo is due on Friday, but we won't be conducting our second lab demo until later. Okay. If I remember correctly, what are there about 5 of you who are going to the Virginia's conference? 1, 2, 3, 4, 5. Today we're going to be talking about momentum-depth relationships, and you'll remember from fluid mechanics the momentum expression, which said that the sum of forces required to hold the system steady is equal to the mass flow rate. And so if we multiply the density times the volumetric flow rate, that gives us the mass flow rate m dot. And so if we multiply the mass flow rate by the difference in velocity as a jet stream, for example, enters and exits a control volume, then we know the force required to hold the system steady. And so we applied this expression to a variety of different situations, most commonly vanes and nozzles and jets. And so here in this case, where we had a nozzle of flow being redirected through a smaller opening and then exiting to the atmosphere, what we did in the momentum expression was we considered the forces outside of the control volume, pressure times area, and treated that as though it was an external force to the right. And we considered the difference in velocity of the jet coming in to the nozzle and going out of the nozzle, and so that's how V2 and V1 came into play. And then found the force that was required at the flange to hold the system steady. But we can apply some of these same principles of conservation of momentum to open channel flow. But instead of pressure, what we're going to have is depth. And that's a substitution we've made a number of times already this semester. And free surface flow, let's say that we've got a channel bottom, and the depth of flow in this case is increasing, but it doesn't necessarily have to increase for a conservation of momentum to apply. I've just shown different depths at upstream and downstream locations to illustrate that momentum principles can be applied even in non-uniform conditions. This first equation that's on board here, this equation is sort of the analogy of what happens when we translate conservation to free surface flow. There's a kinetic term and a static term. And if we look at the units for each of these terms, I'm saying that if you multiply both sides of this expression by gamma, the unit weight of water, then you'll have forces. And that should be pretty obvious when it's in terms of area 1 times the depth of the centroid at 1. Okay, so the units here are going to be meters squared times meters, and if we multiply that by the units associated with the unit weight of water, gamma is newtons per meter cubed, then that gives us units of newtons. So that's a force. Now this expression q squared divided by GA squared. Let's take a look at what are the units for that.
Is it A squared or just A?
A, thank you. It's A. All right, Q squared would be meters sixth seconds squared, because it's cubic meters per second and we squared that. So meters sixth seconds squared. G would be meters per second squared, so meters per second squared, and I put the seconds in the numerator and meters in the denominator because G is itself in the denominator. And now A squared, that's going to be meters squared. And cancel out, we have meters cubed, and so this goes down to meters cubed, and the seconds cancel out completely. And so this is equal to meters cubed. And once again, if we multiply meters cubed by newtons per cubic meter, so multiplied by the units associated with gamma, and that's going to yield just plain old newtons. So what we're adding here, is a unit of force, once we've multiplied both sides by gamma, and we're saying that one can conserve momentum through a cross-section where the depth is changing. So force is the unit weight of a fluid multiplied by the sum of this kinetic flow term and static term. Dynamic force, hydrostatic force. Now, we're going to create a diagram, and once we've got it graphed, two diagrams, once we have them graphed, we're going to talk about what they represent and what they're for. You've seen how to create specific energy diagrams. We've done that a couple of times, demonstrations anyway. For the flow that's described here, flow rate of 15 cubic meters per second, a channel width of 6.5 meters, and various depths, we're going to try and graph the specific energy. Here's the equation for specific energy. And then also we're going to graph the momentum as a function of different depths. And so what we've had previously was some combination of lots of different y values. Each row is some different y value. And then in various columns you're going to be calculating the specific energy associated with that depth and the momentum associated with that depth. And so what are the columns going to be? Well, one of the columns is going to be y. All of these are going to have the same flow rate, q. So q might as well be a column, but it's going to be constant. Every row is going to have the same q. B might as well be a column, but every single row is going to have the same b. There's going to be a variety of different depths. You're just going to choose a wide range of depths, and maybe a range of depths that we can solve over. Let's start at 0.2 and go all the way through 4 in increments of 0.2. So we'll go from 0.2 all the way to 4 meters of depth in steps of 0.2. So the next one would be 0.4 and so on. We're going to need to have, in order to calculate momentum, we'll have a column that's h bar. So that's the depth to the centroid for a rectangular channel. For example, if we have our starting depth of 0.2 meters, what will be the depth to the centroid?
Half of that?
Just half of the depth. Right. All right. We should have a column that indicates velocity, because we're going to need that for specific energy. And I think that's about it. I think with those parameters we can then calculate the specific energy and then calculate the momentum. The momentum function, which will have units of cubic meters. Okay. All right, so I'll let you get started on that. In addition to doing it in increments of 0.2, also do it at the critical depth. So the formula for the critical depth is here. add that in. It's probably not going to land exactly in one of those increments of 0.2. So go all the way from 0.2 to 4, solve just on maybe in the spreadsheet or by hand, find the critical depth, and also find the momentum and the specific energy at the critical depth. I'll be circulating around. When we've looked at specific energy diagrams in the past, what kinds of problems were we solving with the specific energy diagram, where the specific energy diagram is this one that has energy and depth? Remember what types of problems those were?
The water elevation changes.
Okay, elevation. Change. And it was the water elevation was changing
Based on the width changing, volume changing.
channel widths, and also bed static. These are types of problems where energy is conserved through the transition. There are some cases where energy is not conserved through a transition, but there's going to be a new depth. These are examples of gradually varying flow. Sometimes the water depth changes rapidly. And so the momentum depth diagram is used in rapidly varying flow. R, B, F. And so the diagram that we looked at just now, where we have a momentum function versus depth, that's used in a hydraulic jump. In a hydraulic jump, energy is not conserved. In a case like a channel getting wider or narrower, the energy is conserved through gradually varying flow. But in rapidly varying flow, although energy isn't conserved, momentum is. Let's take a look at a couple of types of situations that can induce this rapidly varying flow. In this first example, you'll notice that there are two slopes. One of the slopes is greater than the critical slope, and one is less than the critical slope. The critical slope is the slope that causes critical flow. By the way, I think it's more important right now, rather than to be filling out the spreadsheet, to focus on these. These are sort of the broader concepts, and you're already pretty good at punching numbers in the spreadsheet. But this is new information. So you'll know the characteristics of a steep slope, a slope that's steeper than a critical slope. So notice here that the normal depth is less than the critical depth. That's how we know it's a steep slope here in this first segment. before the change in slope. So this dashed line is referring to the critical depth. Then after the slope transition, the normal depth is greater than the critical depth. And so that's how we know this is subcritical flow that's being caused by a slope that's less than the critical slope. These indications of whether flow is supercritical or subcritical should come instantly to you. It should be second nature. You should be able to diagnose the flow regime based on the slope, the depths, the Froude number, backwards and forwards. It should be the easiest thing in the world for you to know and understand. And if it's not that way yet, then I don't know, flashcards or read through the book another time. But here we've got a steep slope and now a mild slope after that transition. So in the mild slope, there should be subcritical depth, but there's a supercritical depth in the supercritical segment where we've got a steep channel. So there's going to have to be a transition there where it goes from supercritical flow to subcritical flow. And by definition, that kind of a transition is the hydraulic jump. And so here is a hydraulic feature that causes rapidly varying flow. And so if we want to try and find out what will be Y2, we can't use the specific energy diagram, but we can use the momentum depth diagram to find the new depth. We had some depth at 1 with the momentum depth diagram, just to give you an example of where we're headed a little bit later when we calculate hydraulic jumps in more detail. If we knew some subcritical route, this is the supercritical route associated with a less of a depth, and we go through a hydraulic jump, we find the sequent to that. The sequent is the alternate or the conjugate depth that goes along with the same momentum function. Here's another case where you can find a hydraulic jump being formed, and this is what we've got back in the lab. We have flow underneath the gate, and you'll notice that before the gate, the depth of flow is greater than the critical depth, and so here we have subcritical flow. And since the slope is mild, meaning that the slope will be supporting only subcritical flow, but yet water comes from underneath the gate at supercritical conditions, it's going to have to go through a hydraulic jump. And so this is another case where we'll use the momentum depth diagram to find the new downstream depth. What will it jump to? What's going to be the depth after the hydraulic jump is what a momentum depth diagram can help answer. Here's another case where there's a gate, but in this case the slope is steep rather than mild, like it was in case B. So here in case C, there is a hydraulic jump not after the gate, because the gate is forcing supercritical flow, but supercritical flow can be supported by this slope. And so after the gate, it stays supercritical. The depth increases, but then it just sort of levels out to the normal depth when it reaches there. The hydraulic jump is actually upstream because there's pooling. This gate forces pooling to occur upstream of the gate, and the water level increases. The pooling occurs to the point where it crosses that critical depth transition, so a hydraulic jump is formed in order to observe the conservation of energy under the gate, but the momentum depth diagram allows us to find what the depth will be as it jumps through that transition. And then finally, here's the spillway example. We talked about in class last time how flow coming over the edge of a spillway is very fast. It's gaining a lot of energy as it falls down the face of the spillway. So flow for a time is supercritical, but then it has to jump up to a subcritical depth because this slope, being mild, cannot support supercritical flow. And so there has to be a hydraulic jump. RVF stands for rapidly varying flow. GVF, gradually varying flow, is when the flow depth is changing gradually. So here is gradually varying flow. It's anytime the flow depth is changing, but it's not a hydraulic jump. Gradually varying flow occurs after the hydraulic jump here. You notice it jumped to some depth, but then it continued to get a little bit deeper. That's gradually varying flow. There's gradually varying flow after the gate, but before the hydraulic jump. There's gradually varying flow as water approaches this obstruction. And really, the hardest thing we'll do all semester is trying to find out gradually varying flow. Trying to find the depth of flow when it happens very slowly and over a long distance.